Okay. So, let me ask you a couple. I'm going to show you a couple of cool little things about making a list of factors of a number, right? And this isn't prime factorization. I just mean, so there's a difference between if I ask you to make a prime factor tree versus list all the factors of a number, right? So let's kind of do some just to get the feel of it. How are you doing, Green? You're doing good. So list, can you guys see that? List all factors of, all right, Green, you're a little bit. Yeah. 12, sure. This is not a prime factor tree, that's different. So what do you got? 1, 2, 3, 4, 6, 12. All right. Do you guys agree with me that there's a turning point in the list of factors? And what do I mean by that? 1, 2, 3, you have to come up with. At some point, you hit what I call the turning point, which is where you start 1, 2, 3, and then 4 goes with 3, 6 goes with 2, 12 goes with 1, right? So the turning point for this list is around between 3 and 4. Does that make any sense? So here's how you find that. If I knew how to find that, I have to worry about the first half, and then the next half is easy shit. I just have to pair it with the stuff from earlier. Does that make sense? What is the square root of 12 roughly? And the way you do that is what number what number below 12 can I do the square root of easily? Can I do the square root of 12? Does anyone know what that is? Just go for it. The square root of 12. Do you guys know what it is? No. I don't know what it is either. What number do you know the square root of that is just a little below 12? 9. What's the square root of 9? 3. So square root of 12 is approximately 3. And sure enough, where was the turning point right after 3? I don't know if you guys are with me or not about this. Do you guys see that? So for example, if I had to find all the factors of, what do you got, Jeff? 24. Right? So I gotta think. 1, 2 goes in, 3 goes in, 4 goes in, 5 doesn't go in. Now, square root of 24 is almost 5. It's between 4 and 5. Is that cool? So the turning point should be right before 5. And you see, that's exactly what happened, because now 4 goes with 6, 3 goes with 8. Do you guys see that? That's kind of cool. So then I know when I have to stop paying as much attention. The first part of the list is, does that go in? Does that go in? The second half of the list is, pair it with this number, pair it with it. That's much easier, right? Okay, maybe. And that's something, of course, that you don't see very often. You don't get to see that idea. Okay. So that's one thing. Another thing is, what if I asked you, okay, how about 540? Okay, are you excited to do that one? So I could figure out the turning point for this. Not as easily, but you could do it on your calculator, right? What's the square root of 540? Anybody? You got a calculator? Square root of 540? Around 23? Okay, sounds about right. So around 23 would be where this thing would turn around. So what's more daunting about this, of course? It could have a lot of factors. So wouldn't it be good to have a way to know ahead of time how long this list should be? Do you guys agree? So knowing where the turning point, where the pairs start happening is good. But if I knew how long the stupid list should be, I could quickly see if I missed somebody. Does that make sense? I don't know if I missed somebody. If I make a list, I have no idea. But if I knew how long the list was supposed to be, I can see if I missed somebody, right? So let's do this. We'll look at 540 in a minute. I'll put you over here, 540. Let's look back at 12. I erased it just now, but how long was the list? 6. If you break 12 down into prime factors, what do you get? 2 times 2 times 3, is that cool? Okay. I'm going to show you something kind of cool that I show sometimes when I'm teaching students how to factor quadratic expressions. Do you guys remember doing that? X squared minus x minus 12, and you have to factor it. Remember, so you have to find factors of 12 that had to be 1 and blah, 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 the combinations. Yes? So, if I want to find factors of 12, one way to do it is to break it down to its parts and then pair these up in all the ways you can. You can do this in a very organized method. What's kind of a factor that I never really list, but it's always a factor? What is a number that goes into any number? 1. Right? So watch this. This is kind of cool. Let me see if you guys... Can't I write this as 2 squared times 3? Ooh, okay. So this is really cool. I really want you guys with me. So what I mean, let me give you a less technical example of what I mean, and then a more technical example of what I mean. I think, let me try it with a little more disgusting number real quick, just on the side note. So 54, if somebody look at that, maybe they'll say, okay, that's 2 times 27. Right, you might see that. It's even, so 2 goes into it, you get 27. And they go, okay, 27 is 9 times 3. Therefore, 18 times 3 is also 54. Do you guys see how I can reorganize the pieces? Does that make sense? Because as long as all those bits are in it, it still makes freaking 54. I don't care which bits go with which other bits on the way there. Who cares? Does that make sense? Okay, now, coming back to this. Watch this. So, the factors of 12. I could take no 2s times no 3s. What would that be? What's anything to the 0 power? 1. So what's 1 times 1? Holy shit. And then I can just do this. I could do very prescribed. I could go 2 to the 0 times 3. 3, right? Okay, I love it. And that exhausts 2 to the 0 as a first thing. All right, I want you to be with me. So I could either take no 2s and then all the possible 3s. I could take 1 2 and then have no 3s, 1 3. And then I can take 2 2s. 1 3, I'm sorry, no 3s, 1 3. That's all the ways it can combine these parts. You stop for a minute. So if I have a 2, and a 3, I could take none of them, and that's 1. No 2s, no 3s. I could take 1 3, and that's 3, right? I could take 1 2 and no 3s, that's 2. I could take 1 2 and 1 3, that's 6. I could take 2 2s and no 3s. I could take 2 2s and 1 3. Is that the complete list? Yeah. Do you see why there's 6 now? How many options were there for the 2? I can have 2 to the 0 or 2 to the first or 2 squares. How many options were there just for the 2? 3 options. You with me? How many options were there for the 3 in each case? 2. So for every 3 options for the 2, there's 2 options for the 3, 6 total options. I really want this to make sense. So if I have 3 choices for color of an exterior, the external color of a car, and 2 choices for the interior. You guys with me? 3 choices for the exterior of a car, blue, red, and white, I don't care, and 2 choices for the interior, right? How many different combinations can I make Well, for every 3 exterior, there's 2 internal. That's the definition of multiplication. That's 6. There's 6 possible combinations of car I can make. Does that make sense? That's exactly the physical idea we're using up here. 2 options for the 3, 3 options for the 2. I should end up with 6. So what's a shortcut I could do? Obviously, I don't want to do this because that's not really helping me. That's making the list, right? So what were the powers, the second power and the first power? The fact that I could pick none of it. I really want this to make sense. Why did I have 3 options for the 2 when it's to a second power? Because one of the options is none of them, right? So in general, this is really freaking cool. In general, if I have a to the m times b to the n, we'll extend it here in a minute, the total number of factors would equal m plus 1 times n plus 1. All right, let's try a concrete example. Let's do that one we just did, 24. I didn't finish writing out, but 1, 2, 3, 4, 6, 8, 12, 24, right? So how many numbers is that? How many numbers? How many numbers? No, there's 4 and 4, there's 8, right? 8 numbers. 8 factors. Take a minute and prime factor 24 for me. Break 24 down into prime factors. So what do you get? You get 4 times 6 or whatever you want to do. So I get 2 times 2 times 2 times 3. So I get 2 cubed times 3, right? So if I apply the little theorem up there, how many factors would we predict? 1 more than 3 times 1 more than 1. 4 times 2, 8. So we have a way to predict the total number of factors that should show up. What was that number? 540. Okay, let's look at 540. Look at 540. Oh, yeah. Can you guys take a minute and prime factor 540? So let's see, the way I would do it, it doesn't really matter. I just see those first. This will be 2 times 27. 27 is 3 cubed. 2 times 5. So I end up with 2 squared times 3 cubed times 5. Is that what you guys got? So that's 1 more than the total, but we can just extend the idea. So how do you think I handle this? How would you predict the total number of factors in this list? I just kind of keep going, just extend the idea. How would you do it? So here it was 4 times 2, 8, right? 1 more than that power, 1 more than that power. Okay, so what's 1 more than this power? 3. And what's 1 more than this power? 4. And what's 1 more than this power? You just kind of keep going with the idea. So I should get 3 times 4 times 2, which is 24. I should end up with 24 factors in my list. Does that make sense?
I don't get why you would add one more. So total number of factors.
So going back, all right. So going back, so we had 12, right? We had 12, and we broke that down to 2 squared times 3, right?
Mm-hmm.
I could pick 2 to the 0, 2 to the first, or 2 squared. So for this one, I have 3 options. 3 to the first, I could pick 3 to the 0 or 3 to the first. So for that one, I have 2 options. I always have one more option than the exponent because one option is none of it.
Mm-hmm.
That's why it's plus 1 first and then multiply all of them together.
Okay.
How you guys doing? Okay. I'm almost certain none of you have ever seen this before. Right? But it's good to know. It's really good shit to know. But the reason you haven't seen this before is because by the time a student would understand this, you're past doing this kind of thing. So it's kind of like a really cool idea that just never has its time until you get to a class like this, right? And as a teacher, it's better for you to know more than what you're going to teach. You always want to know more behind what you're going to teach. Okay. So let's see. I'm going to have you guys try a problem. I want you to predict the number of factors and then list them. Oh, and then find turning point and then list the factors. Okay, there we go, Jeff. Pretend like you can read that. All right, so what about, let's do this, let's do 100. 100's nifty. So predict the number of factors, find the turning point. Hopefully that name makes sense because it's just a name I just made up. And then list the factors. I don't think the book talks about that square root thing, but just good to know. I'm going to start to catch up to you. So how many factors should this have? 9. 3 times 3, right? 3 times 3. I predict there to be 9 factors. Now, it has an odd number of factors. That should kind of like be interesting. Because the other ones we just did, they had even number of factors, right? Why does it make sense this is going to have an odd one? Because this have a single digit in the middle that goes with itself, of course, right? Because 10 times 10 is 100. And then everybody else is going to pair up. You guys kind of with me? So that makes sense. It's going to have an odd number of factors. What about the turning point? For this one, that's easy. When it comes out to be exactly something, that's the number's going to repeat itself. I mean, obviously, it's a square then. Is that cool? And then you start to make the list. So what you got? 1, 2, 4, 5, 10, good. So now you've got, so there's 4, there's 1, and then the other 4 are going to be the pairs, right? Kick ass. So then this, of course, is 20, 25, 50, 100. Kick ass. Okay, good. So on one level, this is kind of basic, but on another level, I have a feeling that most of you guys have never really seen this before. I thought about it. Okay. Has anyone ever seen any of this before? No, okay. Do you think it feels kind of useful, right? Okay, maybe, okay. You're like, no, Jeff, I gotta count. Okay. All right, so that's that idea. Not too bad. So now let's talk about dealing with a couple of numbers at a time. So let me just say these letters and see the reaction. GCF. Anybody have any connection with GCF? Greatest common factor. Anybody know what it means? Or what it's in reference to?
The greatest number in both the factorizations.
Yeah, the greatest number that's a factor of both numbers, right? Or you could actually do GCF of multiple, not just 2. So it's the biggest number that goes into all of the numbers being considered, right? Greatest common factor. Anybody think about that in terms of factoring algebra stuff? Like if you factor 2x squared plus 4, 2 is the biggest common factor, so you take a 2 out. Right? Let's not go there, I'm sorry. So for example, here's how a question could look. GCF of 3 and 12. I'll start off nice. That one's really obvious, yes? What's the biggest number? Basically, a way to sum this up is, what's the biggest number that goes evenly into both? 3. That's easy. All right, let's step it up just like one notch. Let's crank it up just a bit. What about GCF, Jeff? You know how to make an F? Not just because I'm a teacher, but because it's in my name. 12 and 15, that's not too hard. In fact, you can see that it's the same answer, but let's analyze a few methods for when you know I'm going to throw worse numbers at you. You know they're coming. One thing I want you to realize, well, we'll get there. Real quick, what's the difference of the two numbers I'm considering? That's kind of a key element. We'll see, I'll extend that idea, but whenever you're trying to figure out what goes into two numbers, the first thing I do is I take the difference, and I'll tell you why later, okay? So there's 2 methods, right? This book loves its methods. One method sounds very familiar. It's called the set method. It's actually called the set intersection method. What happened to you, poor little dude? So here's how this works. We're basically going to do what we did earlier. We're going to make a set of all of the, you can do it, Jeff, all of the, good Lord, there went my brain. All the factors of 12, there it is, and all the factors of 15. Gotta love 15, thank you 15. And what do you think the next step would be? So obviously this is really good for a very young student because it's helping them practice with making a set, and then it immediately leads to a process. So what would that process be? And the name gives it away. Yeah, intersect the 2 sets. You're always going to have an intersection that has 1, and sometimes that will be the answer, correct? The GCF of 2 numbers that are relatively prime will always just be 1. But in this case, the intersection, if I intersect these 2, just deal with my horrible notation, I don't care. Intersect those 2, what do you get? 1 and 3, and of course you're going to take the greatest one. Okay, I like it. So that's the set intersection method. if you have a person who doesn't need to practice making a list of factors, you are hopeful there's another method, because this is sort of, that would be the only reason for this, almost, is just because somebody needs practice setting, making lists of factors, and then they go, oh, 3 is the biggest thing they have in common. That's the common factor, greatest common. Everybody cool? Okay. So let's improve on this. Let's make this method better.
Here.
You got some examples, Jeff? Oh, before I do that, I'm just being silly. Method B, which is called the prime, you could do it, buddy, prime factorization method. Actually, let me put this up here, yeah. Prime factorization method. There's no way you can tell what you're supposed to do with that. Well, obviously. So you take 12 and 15. Prime factors, what do you get? You get 2 squared times 3. You get 3 times 5. That's amazing. And then it's basically the same thing as set intersection, but it's more direct, correct? That's an immediate improvement on this. So I don't have to list all the factors. I just have to break it down into its prime factors, and then what do you see? You can just see the common factor, correct? Okay. How are we doing? So let me do this. Let's take some slightly bigger numbers. So what if I wanted the GCF of 40 and you gotta know it, Jeff. Let's do 40 and 88. What? So real quick, how far apart are those numbers? 48 apart. So here's something kind of cool. If you're trying to figure out the biggest number that goes into 2 numbers, real quick, if 3 goes into 2 numbers, don't they both have to be in a list of multiples of 3? That's basically the definition, correct? Give me 2 numbers 3 goes into. 9 and 12, right? 3, 6, 9, 12. They're both elements of the multiples of 3, correct? And everything that's an element of the multiple of 3 is 3 apart from the next guy. It's 6 apart from the next guy up, right? It's some multiple of 3 apart from another multiple of 3. Are you guys with me on that? So, if 2 numbers are 48 apart, either 48 goes into both of them, or a factor of 48 goes into both of them. Does that make sense? Maybe. So for example, 3 and 15. They're both multiples of 3. They're 12 apart. 12 does not go into 15 or 3. 4 doesn't go in, but 3 does. So it's a generally good rule is I'm trying to figure out what's the common factor to 2 numbers. I could just look at the difference. So if I would have given you the GCF of 40 and 42, why is that done? That is done. You are done. What's the difference? 2. That's the only number that could possibly go into both. And it does. So the GCF of 40 and 42 is 2. What about the GCF of 39 and 41? What's the difference there? 2. That's the only number that could possibly go into both, and it doesn't. So it must just, the GCF must be 1, because 1 has always got your back. 1 is like, I got you. If nothing else works, I'm here for you, right? You guys doing okay? Okay. So again, this is not like extra high level stuff, but in a way it is, because it's looking at numbers in a different way than what you're used to. So for this, obviously, do you agree with me, 48 does not go into both. It doesn't even go into either one, right? So either it's going to be 24, it's going to be 8 or 6, or it's going to be some factor of 48. So let's find out what it is. So how do I do it the prime factor method? So let's see. Help me out. You're on your own, Jeff, math boy. Break it up for me, what's it? 20 times 2, I love it. 10 times 2. 5 times 2. So it's 5 times 2 cubed. Is that cool? Okay. And 88, I'll do 8 times 8, which is 2 to the third times 2 is 2 to the sixth. Oh, I'm so smart. Oh no, wait. Jeff needs to get a star. Because I mean, you couple that with the awesome, it's 11 times 8, that's amazing, Jeff. Now I'm really concerned about myself. So it's 11 times 2 cubed, okay. That's a little bit better. So this one is really obvious what the GCF is, correct? What's the GCF? 2 to the third, right? So it's got to be the highest part that's in both. You guys with me? Okay. So this one I have 2 cubed. And sure enough, 8 is a factor of 48, right? Bless you. Okay, maybe. That's sort of like, was that in here? It's funny if it was in, no, I think it was another class. It was like 18, there was an answer to a math problem, it was 1892, and I'd said something about Columbus. And then I went, no, that was 1492. So anyway, that was an exciting day for Jeff, showing off that I'm teaching the right thing, not, and now this is like, maybe you're not teaching, but maybe you should go with history. Okay. How are you guys doing with that? Is that all right so far? Nothing too major? Okay. Blah, 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 blah. Okay. Oh, yeah, good. We did that. So here's where things get kind of exciting. It's sort of related to what I just said over there. Let me see. How do I'm going to take your star away. Yeah, let me do this. Perfect. Let me do this. This is kind of related, not really, but it helps you out with one of the problems on the test that a lot of people have trouble with, which is that 2 divides A, 6 divides B, blah, blah, blah. So if, let me set this up right. If A divides M and A divides N, and we know that M is bigger than or equal to N, okay? So A goes into M, A also goes into N. And M just happens to be bigger than or equal to N. Then A divides M minus N, which is kind of related to what I just said about taking the difference to sort of see where things go. So we're going to prove this real quick. Okay, so this is going to be exciting. It's always exciting when we do conceptual proofs. And this will help you make corrections to your test, by the way. So if I say A divides M, what the hell does that mean? So give me, one thing that happened was I think people had the reverse. It's got to be A divides M means A goes into M, correct? So why does 2 divide 12? What's the quickest way to tell me why 2 divides 12? But tell me, what's that mean? What's 2 goes into 12 mean? 2 divides 12. 2 goes into 12. What's the quickest way to say why that's true? 2 times 6 is 12. That's the quickest way. So the whole idea of divides evenly or goes into or whatever is the fact that you can multiply it by a whole number to get that number. Okay, right? 3 divides evenly into 15 because 3 times a whole number is 15. 3 times 5 is 15. 3 does not divide evenly to 7 because 3 times not whole number equals 7. Is that cool? Okay, so what can I say? So this is the theorem. And it's true. We're going to prove it, right? That's the theorem. So now let's kind of investigate it. We know that this is true. So I can immediately write down that m equals a times something. Let's just say x. Is that all right? You guys with me? Just like 2 divides 12 because 12 equals 6 times 2. So what can I write for this guy? Be very careful. N equals a times, I already chose x, right? And when I multiply x by a, I get m. Now I want to get n. So can I also have an x there? No, because it might be equal, but maybe not. So just pick another letter, probably y, 11, okay. If a number divides another number, that means that that number times something is that other number, correct? 6 divides 48 because 6 times 8 is 48. A divides m because a times something is m. And of course, what's true about x and y, they have to be whole numbers for this to mean evenly. Is that all right? And again, this is where, we go off on this other level of shit because we're like, okay, numbers, oh shit, now we got no numbers, but just ideas. But you can, every step of the way, you can put a numbers in to see what you're really saying. Just like I did with 12 and 6 and 2. You can just kind of remind yourself concretely, what does this mean? So now, how do I investigate this? In order to investigate that, what do I need to create? What's the number that says a divides into? The answer is not 7. Just what does it say a divides into? M minus n. So can we calculate what m minus n is? Yeah. What's m? Ax. What's n? A times y. Does a divide that? Is another way to say something divides something else. It's got to be a factor of that thing, right? Why does 2 divide 12? Because 2 is a factor of 12. Is a factor of this number? Can you take an a out? Yes. So a does divide m minus n because a is a factor of m minus n. So that was great. I love it. I can see your faces. You're all like, that was a bunch of shit, Jeff. So let's try, so that was the proof. Let's just try a few concrete numbers, right? Okay, I'm gonna start us off. Let's look at this in a concrete way. Let's figure out what the hell this is saying. I'm gonna give us one to start off with. So 2 divides 12. Jeff, there you go, buddy. So I've established a is 2, correct? Somebody else give me another thing that's true. So I gave us this. What's this going to be? Anything you want. 24. Holy shit. So 2 divides 12. 2 divides 24. Right? So what's the conclusion say? 2 should also divide. Now, and of course, I have to be, this will be our n, this will be our m, right? Because m is supposed to be greater equal to n. Are you guys with me? So just the bigger number goes first, basically, so you don't subtracting it negative stuff. So 2 is supposed to also divide 12, and of course it does, right? That is not a proof because it's too specific. Let's try something a little bit freakier. 6 divides 18. 6 also divides 66. Sorry, I'm giving myself shit about me. I just can't get over that. Therefore, what's supposed to be true? 6 is supposed to divide what? So I gave us this. I established a is 6, and I gave us 2 things, right? And what's the conclusion say? 6 is supposed to divide. I'm sorry, you might have said it, but I can't barely hear you. 48, there it is. Okay. Does 6 divide 48? Yes. I like it. Okay. By the way, another way to look at this, let me see. 6 divides 18, so isn't that like 18 over 6? 6 divides 66, so isn't that 66 over 6? If I subtract these, aren't they like denominators? Right? So I feel okay with these fractions because they're like denominators, so. What do? They're like denominators, so what can I do? Yeah, just subtract. Now, in general, I want you to make, okay, just go with me for a second, okay? I really want this to make sense. So in general, if I have two fractions and I subtract them and they have like denominators, it doesn't matter, Jeff. Make that a 5, sure. The result isn't something that works, but do you see how the two numbers that were given to me didn't go in evenly? So the whole point of this is these two go in evenly. So isn't this a whole number? And isn't this a whole number? So of course, when I subtract the tops, it's the same thing mathematically. So of course that also is a whole number. So that's all that's saying. If you have a number that goes into something and a number that goes into something else, then the numbers go into their difference. And you can see that through fractions. Fractions help sometimes. Okay. I don't know if you guys are with me. So what the hell does this mean, Jeff? My God. Okay. What this means. I like to say things as I see them in your eyes. Oh my God, Jeff. So now we have a process we can use. So now let me make this into a theorem about GCF. Theorem. The GCF of AB, where A and B are whole numbers, and B is bigger than or equal to A. Actually, it doesn't matter. A is bigger than or equal to B, sure. This will equal the GCF of A. Now you've done it the wrong way, Jeff. I love A minus B, B. It's pretty much built off of what we just did. So if 6 goes into 48, then 6 goes into, that means that 6 went into the difference of these two things. So if I'm looking for a GCF for 18 and 66, the answer will be the same as the GCF of 18 and 48. And it's built off of this idea over here. What does GCF mean? It's the biggest number that goes into two numbers, correct? So let me give us an example. So if I have GCF of 80 and 1400 and, now let's not go there yet, Jeff. 228. Sure, I like it. You all agree with me, at least 2 goes into both numbers. So maybe there's something bigger. Do we know what that bigger number is yet, if it exists? No. But there is a number that goes into both of these, correct? Which means that same number will go into the difference of these two. That's what the thing is we just did. Is that cool? So I can kind of create a simpler problem by applying the theorem. So instead of answering this crazy thing and making freaking lists of factors for these crazy numbers, I can just say this equals 80, 228 minus 80. What is 228 minus 80? I don't trust you, Jeff. Yeah, okay. And then guess what I do? Do it again, right? So this equals the GCF of 80. So whatever the bigger number is, you just keep subtracting the other one. lecture must suck today. Everybody's leaving. So 148 minus 80. Okay, feel pretty good. Now what would it, now the big one's 80. 80 minus 68. No, Jeff. 80 minus 68. 12. 68 minus 12. Okay. That will work. Can you already see that we need a way to shortcut this? Do you guys agree? What do we keep doing? What operation am I repeating over and over and over again? What operation are we doing over and over and over again? Subtraction. What is repeated subtraction? What's a better algorithm to use instead of subtraction repeatedly? What can I use instead? Division. Division is repeated subtraction, correct? So let's see. Can we suffer through this? I can do one thing real quick. Couldn't I subtract multiples of 12 so I can subtract 60? That's one thing we can do. You see that? 12 and 8. Is that all right? No? So I subtracted 12 5 times. So I subtracted 60, right? And you can see why division is going to work, because that's what division does. And then if I wanted to, I could keep going. GCF of 4 and 8, and then GCF of 4 and 4, and of course that is 4, right? You could have seen that maybe here, but you know, what the hell? You could just keep going until you get to the same number. What does this look like if I use repeated division instead, so I don't go insane? So if I start with 80 and 228, 80 goes into 228 how many times? Twice, right? Twice, 160, and then you get whatever. What do you get, 68? I don't trust myself. So remainder 68. So the 2 times meant that I can subtract 80 twice here, right? And the remainder is what would be left. And that's basically here. See that? So we got to this step quicker. I subtracted 80 twice, and that's where I am now. Are you guys kind of with me? So now it would look like this. You could write that, or you could just realize, now I'm going to take 68 and divide it into 80, but that only goes once, right? But if I do that, now my remainder is going to be 12, right? So now I am here. See that? Okay, maybe you guys see that? And then again, I could do 12 into 68. That goes 5 times, which is exactly that last thing I just did, because I did 5 12s, right? So now I am here. Okay, maybe. Okay. But do you see how this is a beautiful little example of how math builds, right? We make a process, we step back and we go, I don't want to do that all day. All right, let's improve the process. And we're like, okay, that's a little better. I still don't want to do that. And so we improve it. And that's where the division algorithm, remember all those intermediate algorithms, getting a little more efficient. Okay. You keep going, you're going to get the same answer. Is that cool? In fact, let's just keep going. What do I have left here? Now I'm at the stage where I have 8 into 12. That's once. So now I got a remainder 4. 4 into 8 goes twice with no remainder. So the last number that divides in evenly is the common factor. It's the greatest common factor. Okay. Maybe. Okay. Let me show you an example where, well, what do you guys think about this? About what, Jeff? I don't know, Jeff. Sure. Okay. So I want to show you why the first thing you should do is to see how far apart the two numbers are. Can somebody really quickly tell me how far apart those two numbers are? 78. Does 78 have any connection to either of those two numbers? Can you see it? Yeah. So this is 39, and then two more 39s, I get to this guy, right? So doesn't 39 go into 117? Isn't that like 117? If I did a list of 39 multiples, 39, then it would be 78, one more 39, 117. Right? So this is two steps away. Do you see? So I don't have to do any work. The answer is 39. So I always take the difference of the two numbers I'm looking at to see if the answer is already just staring me in the face. I don't know if you guys are with me on this or not. Okay. All right. You guys seem the appropriate level of excited? Okay. Blah, 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 blah. Okay. Oh, yeah. Here we go. So just to kind of summarize what we did over there. Here's another little theorem. That's kind of an improvement on our earlier one. GCF AB with A and B whole numbers. What else? A is greater than or equal to B. A equals BQ plus R. So what the shit is that? What the shit is that, Jeff? So if A is bigger than or equal to B, do you all agree that means that A is some multiple of B plus maybe a remainder? So every number, here, I'll pick 7. Somebody give me any number bigger than 7. Any number bigger than 7. 27? Thank you. Okay. Can you find two numbers? One you multiply by 7 and then you add on top of that and make it 27. Can you do that? 7 times something plus something equals 27. Can you figure out what those two things are? Do you see why I use the letter Q there and the letter R? How do you figure out what it takes to multiply a number by to make it another number? Don't you just divide them? And the remainder would be in case it doesn't go in evenly, right? So what is 27 divided by 7? 3. And then what do you have to add on to 21 to make it 27? So the remainder would be 6. So all this is saying, if A is bigger than or equal to B, I can always find this. If A equals B, Q is 1, R is 0. Still works. You guys see that? Okay. So therefore, if I have this situation where those things are true, this equals the GCF of AR. Of course you wrote that the wrong way, Jeff. All my notes are the other way around. I don't know why I switched that. RB, that's better. A was bigger. That's pretty much what we just did. So just to show you what we just did. Make sure you guys at home saw that. I think I see the whole board. On this first step here, on this very first step, this became, so I subtracted two 80s and I got 68. So this became 80, 68. This became this number, comma, remainder. So then you would just keep going, right? I love you guys. All right. So again, every step we've taken has built. I think you guys were all sort of with me with the subtraction algorithm. The division just makes that more efficient. And then this thing is just, it always looks worse when you try to capture it generally. Poor little equations always look worse than actually using them are, because equations have to capture every situation. Makes it look worse. So, you guys try this problem. Oh yeah. Oh, that sounds good. I'm sorry. Did you guys get all that? It's in the book too. Okay. Try this problem using this algorithm we just created. GCF. What are your fantastic numbers, Jeff? 840 and 3432. Oh yeah, okay, that's cool. Oh. So just make sure it was on the right track. I'm just going to do this. Oof. Does that look right? Yeah. So real quick, is everybody cool with that first step? So what does this become so far then, based on this step? So this becomes GCF of what? Oh, this is great, Jeff. The smaller number stays the same. And what did we cut the bigger number down to? We subtracted 4 of these from the bigger dude, and now what is he? What's left? That's why the remainder is awesome. It who remains is the 72. But I can kind of shortcut this. I don't even have to write that. So I could take the remainder and divide it into, I could just redo the process as if this was the original problem. If this was the original problem, wouldn't I divide 72? So I can take the remainder and divide it into him. This is fun, Jeff. No. So if I do this, I think it's 11, right? 792. So then you get 48. Is that cool? Okay. So now remainder 48. So now I'm going to take 48 into 72. You don't even have to waste writing what the GCF statement is now. You just kind of keep going, right? 48 into 72. Goes only once. Now I'm at 24, right? So once your numbers get really kind of small, where are we at now? Now we're at GCF of 48 and 24, right? And of course, do you guys see what that is? How is 48 related to 24? It's double. So what number goes into both? 24, right? 24 goes into itself, and you just told me that 48 is double 24, right? So you don't have to keep going until you go insane. Once the numbers are small enough, you can just kind of stop and go, okay, I can figure this out now. But it just cuts the numbers down for you, right? Okay. Crazy sauce. It's like a little golf pencil there. Oh, all right. Last idea for the day. What do you think comes right after GCF discussion? I don't know if you guys. Least common multiple, which is actually the exact same idea as LCD, least common denominator, right? It's just called LCD because it's a denominator. It's just not a number out in the world. It's underneath something. So let's talk a little bit about that. We're almost done for today. This is another reason I wanted today early, is because I knew this was going to be very exciting, and you'd all have to have some time to calm down. So least common multiple. So let's just start off with a straight question. So let's go back to 12 and 15. Good old 12 and 15 where we started. I still have the same two methods, but now, of course, they have different looks to them, right? So I still have a set intersection method. But now it's not about creating a set of factors, because I don't care about a greatest common factor. Now I want to make a set of what, because I'm encouraged about least common multiple. So I want to make sets of multiples, right? So for 12, tell me the multiples of 12. 12, 24, 36, 48, 60, 72, 84, 96, blah, blah, right? So you can see how this method can get horrendous. If the correct answer was in the thousands, screw this method, right? But again, you're very careful about the kind of problems that you're going to have students work with. You make sure it's not something where the list is going to become stupid big. And of course, 15, 30, 45, 60. Why can I stop? Because. So now the idea is the least common multiple. Greatest common multiple would not make any sense, because that would basically be infinity, right? So least common multiple is the first place they meet. There you go. Now, real quick, I'm going to show you the second method, but I'm going to show it to you in fractional form because I am evil. So what if I had to do 1/12 plus 1/15? Right? And if anybody's thinking 2/27, keep that to yourself and never think that again, right? I have had people in very high levels of math basically tell me that that's 2/27, and then, but what do I need, of course, before I can add those fractions? Common denominator. Of course, why do I need it? What's 2x plus 3x? 2x plus 3x? 5x. What's 2x plus 3y? 2x plus 3. I don't know what the shit that is, right? 5 yellow. So I have 1/12 plus 1/15. That is exactly like 1x plus 1y. I can't put that shit together. They're not like terms. So LCD is exactly the same idea as like terms. If I have 1/3 plus 2/3, that's freaking 3/3. Just like 1x plus 2x is 3x, right? You guys with me? Okay, we're not going to suddenly, that's the most I'll talk about fractions directly. To make an LCD, which is the exact same thing as LCM, I want the number that both 12 and 15 can become. What I show my students is break these down. We've done 12 today a few times. Now watch. I don't have kids. It's probably a good thing because, for example, if I gave one kid too much ice cream and the other kid not enough, and they look over and like, oh, you got ice cream, I would just eat all the ice cream and say, get out. But so it's probably a good thing anyway. So what does that ice cream have to do with this? So I gave one kid this and one kid that. So this kid got some vanilla fudge on his chocolate fudge on his vanilla ice cream, and he got vanilla ice cream and sprinkles, right? So they're both, I don't want sprinkles, I want fudge. So you're going to give them both what they're missing, correct? So what is this one missing that he's got? A 5. And what's this one missing that he's got? 2 squared. And of course, what is 5 times 12 and 15 times 4? They are 60. That's the least common, that's 60, right? Least common multiple, 60. So there's a prime factorization method for this also. So you don't have to make fractions. Let me show you what it will look like. So the LCM, so method 2 is prime factorization. LCM of 12 and 15. You would take 12 and you would prime factor it, and you take 15 and you would prime factor it. And then the answer has to have 12 in it, correct? The answer's got to have 12 in it, and it must also have 15 in it. So what am I missing in what I've listed so far that 15 has in it? Am I missing a 3? No, I'm just missing the 5, and that, of course, is still 60, right? So still this idea of give it what it's missing, right? So let me ask you a very interesting question. Like, for a change, be quiet. What is the LCM of 2 squared times 3 to the 4th times 11 times 17 squared and 2 to the 5th times 3 cubed times 17? First thing I want you to not do is, dear God, don't multiply that shit out, right? It's already been factored for you, right? So I want the least common multiple. So there's a bit of a shortcut that I could use here. I want the smallest thing they can both multiply up to be. So for example, which one has more 2's? Which one has more 2's? And you guys all cool? You see this is one number and this is another number, right? I just have 2 numbers in there. They're just already broken out. This guy's got the most 2. So the least common multiple is going to have 2 to the 5th in it, because I can make him become 2 to the 5th easy. Is that cool? How many 3's will the LCM have in it? Can anybody see the shortcut now? Could I make this become that? Could I multiply this by something, number 3's, to make it the same as that? How many 3's do I multiply this guy by to make him have the same 3's? How many 3's does this guy have? 4. How many 3's does this guy have? How many does he need? So I can make both of them have 3 to the 4th. Is that cool? So LCM is all about what can you multiply both of them up to be. Can I multiply this by something? Multiply by a whole number and make it become just having 3 3's. Shit, no. So what's the shortcut when they're already prime factored for me? I just take the biggest power on each base. Because I can give him a 3 and it's 3 to the 4th. I can give him 3 more 2's and it's 2 to the 5th. The whole thing is, what can you multiply both of them so they're the same thing at the end? So that translates into, take the biggest power on every base you see. So 11, he doesn't have an 11, but so the biggest power of 11 is 1. And of course, the biggest power on 17 is 2. So that's the answer, right? And how do you check it? Can you find all of these here? Yep. Can you find all of these here? Yep. Okay, I like it. This, it still could be wrong because maybe you gave it too many of something, but at least they're both in there. Okay, maybe. So watch this. One last thing, I think, because you guys look, I don't blame you. You look a little drained. You look a little like over it. Besides already having an LCD, and I know I'm talking about fractions a lot, the next best situation to be in is this. Why is this a really good situation to be in when I'm asking about LCD? Why is that much better than, I don't even want it to be, because let's make this 15, sure. Why is that much better than this situation here, the one we have over there? This situation is so much better to be in. Because do these share anything? Do these share any factors? 4 and 15, do they have any of the same factors? 4 is made up of what? 2's. 15 is made up of 3 and 5. Do they share any factors? Remember what I called that? Relative to each other, they are prime. They're relatively prime. So what kicks ass is if I'm trying to find let me just make this into an LCM question. If I'm trying to find the LCM, Jeff, LCM of two numbers that are relatively prime, the answer is them freaking multiplied, correct? Does that make any sense? If I make a list of multiples, of course they're not going to overlap until I get to them multiplying each other, because they don't have any factors in common. Until I multiply them by each other, that's the first time they're going to have stuff in common. Does that make, or have enough in common? Does that make any sense? Maybe. So, watch this. If I see, let's just do this. LCM of 6 and 8. Is the answer 48? Why can't I just multiply them and get the answer? They're not relatively prime. What's the biggest number they have in common? 2. Is that cool? 2 is the biggest number they have in common. So if I do, this always works, by the way. If I multiply them, but divide by the number they have in common, I will always get the right answer. Why does that make sense? Because if I do 6 times 8, didn't I use 2 2's? Doesn't 6 have a 2 and 8 have a 2? I didn't need to use both. I just need 1 in there. Does that make sense? So of course I'm going to divide the extra 2 out. Maybe. Okay. So how can I make this more general? Well, when I said, what was 2 again? What was 2? What was 2 to this? Where'd 2 come from? Tubular. So if you multiply the 2 things and divide by the greatest common factor of them, you will always get the correct LCM. So normally when I teach students how to work with fractions and find LCD, I show them the method where you break it down and you give them what they're missing. And then eventually I say, did you notice on this problem and this problem, did you notice something? And we talk about it, and then we develop this. I don't ever write it like this, and I don't even teach that level anymore anyway. A little tear. We're not allowed to. Whatever, California. So that's a known thing for you now. So now you know that. And you're all like, I feel much better for knowing this. That's enough. I'll let us out of here a little bit early, so don't get used to it. It's not excessively early, it's just a little bit. So you have any questions on your